Hello, my name is Noson Yanofsky. This is Theoretical Computer Science, and this is a class, and in this class we use Michael Sipser's book, Introduction to the Theory of Computation. Today's lecture is just going to be a general introduction to what theoretical computer science is all about, and we're going to go on from there and do other interesting things. Okay. This class is an interesting class. You spend your whole life learning what computers can do. You can spend your whole, not your whole life, but your whole education learning what computers can do. In this class we're going to learn what computers cannot do, and we're going to get into the nitty-gritty of what computers are all about. Okay, what's a computation? What does it really mean? It's a little bit more of a mathy class, but it has ideas in it that are central and very, very interesting stuff. Okay, so that's what we're all about. Just one thing about this class, the class builds, as opposed to different classes where you teach different topics, every week is a different topic. This class builds. In other words, what we learn on the first week, we're going to use for the rest of the semester. And we need it for the second week, and which is going to need it on the third week, etc., etc. So if at any point you're lost, you can't just say, oh, I'll start next week and do something else. You have to go back and figure out the stuff earlier. Okay. So, what's theoretical computer science? Theoretical computer science asks what a computer can do and what a computer not do. The book on theoretical computer science can be split into three parts. But before that, there's a little introduction to the book, which you are required to know, which has the preliminaries, which you probably learned when you took a discrete structure, discrete math class. You learned that. What's a set? What's the operations of sets? What's logic all about? What a function's all about? All that stuff is prerequisites for this theoretical computer science. So that's part 0 of the book. Okay, and then there's 3 parts to the book, which corresponds to 3 different parts of theoretical computer science. And this class is kind of a survey of those 3 classes. We do a little of the first part, we do a little of the second part, we do a little of the third part, and that way we get a feel for all of them. And you can go deeper into each and every one of those 3 parts on your own, not with the book, not with the class. Okay, so let's go through these 3 parts. The first part is called formal language theory. Formal language theory. Formal language theory is a very interesting thing. And what it's about is as follows. The relationship between a machine and the language that machine understands. Okay? So let's put this a little bit carefully. A very complicated machine should be able to understand a very complicated language. A very simple machine should be able to understand a simple language, and we can go the other way around. If you have a simple language, even a simple machine can understand it. If you have a complicated language, even a more sophisticated computer needs to do it. Okay, so there's this relationship between machines and computers, and we're going to spend a few classes going through this complicated relationship. I just want to say, it works like this with human beings also. Okay. The language that a 3-year-old understands is much simpler than the language that a 30-year-old understands. Okay? Because the 3-year-old's brains are not as complex and as deep as the 30-year-old. And the 30-year-old can understand a lot more, can deal with a lot more. And not talking about intelligence, just the amount of programming that the 30-year-old has as opposed to the 3-year-old. Okay, so there's this relationship. Let me give you another example. A soda machine is kind of and we're going to go through this example in depth, a soda machine is kind of a machine that understands the language of 35 cents. Let's say the soda machine costs 35 cents. Well, to get that soda, you need to put in 35 cents. You can put it in nickels, you can put it in dimes, you can put it in quarters, but it has to get to that soda machine. So a soda machine is a machine that understands the language of 35 cents. Okay. We're going to see other things. What we're going to do in this part of the class is we're going to talk about a certain hierarchy of machines, more complicated, more complicated, more complicated. We're going to start with a very uncomplicated, and corresponding to that, we're going to talk about a hierarchy of languages, more complicated and more complicated and more complicated. Okay? This is summarized in a review sheet. Those of you on the YouTube might not have it. Maybe I'll put a link to this sheet. Okay, and I just want to read it with you. Regular language, context-free language, context-sensitive language, RE. These are the types of languages. These are the types of machines we're going to be learning. Finite automatons, push-down automatons, linear bounded automatons, Turing machines, things like that. Okay, and if we're going to talk about languages, we also have to talk about grammars. So we'll talk about grammars and things like that. So, very nice hierarchy. We're going to spend a lot of time doing that. Let me just say, this relationship between language and machine, you sometimes hear advertisements when they tell you that you should improve your vocabulary. Okay, if you're going for a job interview, you should improve your vocabulary. Why should you improve your vocabulary? Because people judge you by the language that you use. That's very true. So what that advertisement is trying to do is saying, hey you, we can trick people. We can up your language so that people think that your intelligence or your mind is better. Okay, and people do judge you when you go for a job interview. So that's this thing that they're playing with this idea of the relationship between mind and language. So they're saying up your language so that people will think that your mind is up also. And again, you see it with different people with different levels of education. Their language is usually different. Okay. Okay, so we're going to spend a lot of time doing formal language theory. That's what we're going to talk about in the beginning. The second part of the class is called Computability Theory. Okay, Computability Theory talks about what can a computer find. Now, I don't want to talk about baby computers anymore. I want to talk about a regular computer, and we're going to formalize what we mean by that. But what can a computer compute? And more importantly, what can a computer not compute? Okay, what can a computer not be able to do? Okay, so we're gonna deal with these issues. Now, there are a lot of things that a computer cannot compute, and you all know them. For example, a computer cannot really compute what tomorrow's weather is. A computer cannot compute what tomorrow's lottery numbers are. Your computer cannot compute what the stock market, where the stock market or where particular stocks will be in 3 weeks. Because if a computer can do that, then we would figure that out. We would use those computers. Okay, so there are those things that computers can't do, and we all know that those things computers can do. But there's other things that computers can't do. So, for example, a computer can figure out if a picture is pretty or not pretty, or a painting is pretty or not pretty. A computer can figure out moral dilemmas. You know, what should it do? In fact, most of the movies, science fiction movie, a large part of science fiction movies are about computers who don't show any morals and they take over the world, etc., etc. So you've seen a lot of that. Terminator, Westworld, etc., etc. Okay, so now you can say, oh, a computer can't do that because there's no objective answer to these questions. Whether a picture is beautiful or not, there's no objective answer to such a question. or whether or not you should do a certain action, there's no objective answer to that question either. So that's why a computer can't do that. Okay? And that's a legitimate answer. The thing is like this. What we're going to do is we're going to find certain problems that computers cannot solve, and they have objective answers. There are objective answers to these questions. There are yes-no questions called decision problems. They have objective answers, but a computer can never figure them out. Okay? And the famous one is called the halting problem, but we'll talk about a lot of other problems that computers cannot answer whatsoever. But we have to wait for a while. Okay, and the third part of the class is called Complexity Theory. Okay, and that doesn't ask what a computer can do and what a computer can't do. That asks what a computer can do efficiently and what a computer cannot do efficiently. Now, in other words, what can a computer do within a reasonable amount of time? Now, you saw a little bit of this when you took a class in analysis of algorithms, okay? And I have some videos about that too, okay? And where you analyze how long does it take a computer to do this, how long does it take a computer to do that, okay? It takes time to analyze those types of, to solve some problems. But we're also interested in what can a computer not solve efficiently. And there we get into some very interesting things, problems that take centuries or very long times to solve, and we want to talk about those problems, and we want to compare those problems, and we want to get a handle on them. So that's what's done in computability theory. Again, complexity theory. Again, complexity theory is like advanced analysis of algorithms. Okay. Another aspect of complexity theory is to actually categorize problems that we deal with and talk about them. So one of the big questions we're going to see here is this famous question called P is equal to NP. Okay? When we go to chapter 7, you will understand this question. Okay? And we're going to see famous problems like the traveling salesman problem, and the knapsack problem. These are famously hard problems, and we'll see why are they hard and what takes them so long, etc., etc. Okay, so again, complexity theory is like advanced analysis of algorithms. Well, not advanced, but it's not harder, but it just it does the same type of things. They analyze and classify problems. I'd like to put this all in context with a little picture. And the little picture is somehow drawing this hierarchy of problems. Okay? And so the lowest level is formal language theory. Okay? And these are easy problems. So easy that they can be solved by a baby computer. Okay? So those are somewhat easy problems, things that a baby computer can do. And again, we'll see what the definition of a baby computer. Okay? Another level is somehow what analysis of algorithms deals with. And those are problems that are used every day, searching, sorting. That's why that class, analysis of algorithms, is such an important thing. Searching, sorting, matrix multiplication, all those things. Those are problems that a computer deals with. Those are problems that a computer deals with every day, but they're easy to solve. Okay? As opposed to that, harder problems are what's dealt with in complexity theory. These are problems that a computer can do them, they just can't do them efficiently. It takes a long time for them to do them. It could be centuries, years, or something like that. So those are even harder problems. So again, easy problems, regular problems, hard problems, and then we have up here, even harder, we have computability problems. Computability theory, namely problems that a computer just simply can't solve. Okay, they're so hard that a computer just simply cannot solve them ever. Okay, so that's some type of hierarchy of the types of problems we'll see. And again, I mean, we're not going to see any analysis of algorithms, not a lot of it, but you've probably seen some of that. But we will see all of these, and so it's a little bit different. By the way, this is something that looks like a little out of place. Complexity first, and then computability theory. I'm sorry, we first learn computability theory, then we do complexity theory, and you'll see why we have to do that much later on, why we needed to do it in this order. So that's that. Now I want to spend 5 minutes, 10 minutes, since the first part of the class and the entire book is based around languages, so we're going to talk a little bit about what languages are all about and things like that. Okay. Okay, so we need some definitions. We're going to go through 3-part definition. We're going to say what a word, an alphabet is, what a word is, and what a language is. Okay, so definition. An alphabet is a finite set of symbols. Okay, and we usually write an alphabet like that. Okay, our main alphabet is A, B, C, D, all the way to Z. That's called the Latin alphabet. But, you know, if you're Russian, you probably have symbols like this. Okay, lots of different symbols. That's what an alphabet is. An alphabet is a finite set of symbols. Okay, we in this class are not interested in languages, natural languages that human beings speak. We're interested in languages that computers speak. And for that, mostly we're going to deal with this language. Computers speak with electricity going through a circuit, electricity not going through a circuit. Okay, and just to make things a little bit more interesting, sometimes we talk about this alphabet, A, B, or ABC, or something like that. And we deal with how computers figure out things. So that's the definition of an alphabet. Okay, great. Let's talk about words. What's a word? Definition. A word. Now, before we talk about that, before we talk about that, let's talk about this. If this is an alphabet, then this is pairs of letters. Okay? We sometimes write that as that, sigma squared. Okay? And if this is an alphabet, then we can talk about triplets of letters, and we can talk and we could talk about that. Those are triplets of letters. Those are sequences of letters. So, for example, cat. If you're talking about the Latin alphabet, you have cat, you have bat, you have car, you have ran. Those are 3-letter words. Okay? We could talk about 2-letter words, etc., etc. We can also talk about n-letter words. Okay? N-letter words. Words that have length n. Okay? And in this class also we're going to talk about a 0-letter word. Now, what's a 0-letter word? Well, that's like a set that contains nothing. It's a set, even though it has nothing in it. Okay, so that's the empty set. You know about that from finite structures. But the empty word is going to have a special symbol, and we call it that. That's what the book calls it. It's a special kind of epsilon. It's a letter, kind of, but it has no length. Okay, so just like you have the empty set, which is a set that contains nothing, this is a letter that's not really there. Okay, and we're going to spend a lot of time dealing with it. Great. Now let's tell you, we're also interested, okay, definition. A word in sigma is a finite string of symbols from sigma. It's a finite string of symbols. A word is a finite string of symbols. Another way of saying it is a member of sigma star. That's the set of all words. So a word is a member of this. Now what's sigma star? Okay, sigma star is, that's like, can be anything whatsoever. So this is the union of n greater than or equal to 0 of sigma to the n. So this is the union of 0 words, we have that. 1 word, 1 letter words, we have that. 2 letter words, 3 letter words, 4 letter words, as much as you want. So that is the set of all words. Okay, great. Now we go one step up. And we talk definition. An alphabet, a language is a set of words. A language is a set of words. A language is a set of words. Okay, in a certain alphabet, it's a set of words. Okay. Which makes sense. So the English language has something like 150,000 words, but that's fine. Okay, so let's do some examples. We're going to talk about natural languages for a minute, but then we're going to talk about, what we're interested in computers. So if you have the alphabet, the Latin alphabet, A, B, C, all the way down to Z, that's the Latin alphabet, and then we could talk about the set of all words in this alphabet. And then we could say, what are some languages? Well, what's a language? It's a subset of words. So the classical example is English. English uses this alphabet and does it very nicely. Okay. Other things, French. French has a lot of symbols added to it, accents, but it's still basically this. Spanish also uses this, okay, and a few others, okay. Okay, I want to talk about some others. Turkish. Turkish is basically, in the 1930s, Mustafa Kemal Ataturk said, okay, he wants to use a Western language. He didn't really change the language, but he changed the alphabet. The alphabet was Arabic, okay, and he changed it to Turkish. He put in a few umlauts, etc., etc. Polish is a Slavic language, okay, but pretty much because it's a Roman Catholic language, they changed their alphabet, or they use the Latin alphabet. And one other place that's not really well known. Okay, in the Mediterranean, there's a city. There's an island called Malta. They have their own language called Maltese, which is a variation of Arabic in some sense, but they use Latin letters. So Maltese is basically Arabic with Latin letters. Okay, that takes care of that. That's a nice example. If we want to talk about Cyrillic, that's another alphabet. Okay, Cyrillic is another alphabet, which, like I said, is uses. Look, Russian is an example. So. Okay, I don't know Russian letters, but basically that's it. So if you want to talk, you could talk about the set of all words in such symbols, and Russian is an example of a language there, and Ukrainian, Belarusian, Bulgarian, this written thing. Okay, let's do one more. The Arabic alphabet, A, B, G. Okay, I'm not going to write it because I don't know it, but so you could talk about the set of all words in Arabic letters. Okay, and then you could talk about Arabic. Okay, Arabic obviously uses Arabic letters. Okay, and what else? Urdu. Urdu uses Arabic letters. Okay, what else? Farsi. Persian uses Arabic letters. Okay, so different alphabets, different alphabets, different words, different languages. Okay, great. We're not interested in any of these. The types of languages that we're interested in are things like this, or things like this. Okay? Okay, well, let's just stick to this for a second, and we can ask as follows. Here's a language in this alphabet. It consists of words such that the number of ones is prime. Okay, so here's a typical language that we will be dealing with. Okay, so let's do it. So let's just look at some words. 0, 1, 1, 0, 1, 1, 0 is, that's 4 ones, is not a member of the language. It's not in our language. As opposed to that, 1, 1, 0, 1, 1, 0, 1 is a member of the language. Because that has 5 ones, and 5 ones is a prime. 1 is not a prime number, so that's not in the language. Okay? And the empty word is not in the language because it has to have a prime number of ones. Okay? 1, 0, 1, 0, 1, 1, 1, 0, 1, 1 is a member of the language. It has 7 ones, therefore it's in the language. Okay, by the way, we could start asking, how would we write a program to determine what's in this language and what's not in this language? Well, very simple. We take the input, we count, we have a certain counter, and count how many ones there are, and then we have another program, or we have another subroutine to tell if that number is a prime number or not. Okay? And it could be done fairly simply. Okay? So that's doable. Let's do another one. L equals L, those words such that there are 3 twice as many zeros as ones. There are twice as many zeros as ones. Okay, so let's do something. 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0. Okay, this has 4 ones and 8 zeros, so this is in the language. Okay, 0, 0, 1 is in the language. 0, 0, 1, 0 is not in the language. Okay, because this has 3 zeros and 1 1. Not good. Okay, so we can have different things like that. Let's do one more. L such that word, such that the length of the word is less than or equal to 38. Okay, that's the way we write the length of the word. Okay, so 0, 0, 1, 0 is in this language because the length is 4. 0, 0, 0, 0 is a member of the language. The empty word is a member of the language. Okay? It would be a pain in the neck to write a word that's not in the language because it would have to have at least 39 letters. Okay, question. How many words does this language have? Some of those languages that we dealt with are infinite. By the way, all natural languages, English, French, Spanish, Russian, Maltese, Turkish, those are all finite. Finite number of words. Can't have an infinite number of words. Human beings can't know an infinite number of words. That thing with primes, infinite number. Okay? The things with twice as many zeros as ones, there's an infinite number. All the words, you could have 6,728 zeros and 3,000 ones. Okay. How about this? This is a finite set. Question, how big is the set? Well, let's see. I could have words of length 0. I'm going to write that as that. I'm going to have words of length 1. There are 2 words of length 1, 0 and 1. Okay. I'm going to have words of length 2, 0, 0, 0, 1, 1, 0, 1, 1. Words of length 3, all the way to words of length 38. Okay. And how much is this? Turns out this is 2 to the 39 minus 1. Okay, so that's how big this language is. Okay, great. I'd like to talk about one thing that's not here. I'll take a second. Okay, finished. So this is our introduction. This is what we're going to do the rest of the semester. We're going to talk about a language. We're going to talk about how complicated the machine is for that language. We're going to talk about the machine, and we're going to ask how complicated is the language for this how complicated is the machine, how complicated is the language. Again, one determines the other. Okay? For example, that thing with twice as many zeros as ones, how would you write a program for that? Well, very simple. Go through the word, add up how many zeros you have, add up how many ones you have, see that one is twice as the other. Now that's a little bit simpler than finding out if a number is prime. So one language is a little bit simpler than the other language. Okay. Okay, I'd like to finish off with just one interesting thing that has absolutely nothing to do with formal language theory, has nothing to do with theoretical computer science, but it's an interesting fact about human beings. Okay? Okay, this is a bad drawing of the Mediterranean. This is Italy, this is Greece. Let's write it. Italy, Greece. Okay. And this is Africa, this is Europe, etc., etc. Okay. So, a little historical thing. Every single culture of human beings has a spoken language. We all speak. We've all been speaking for a long time. Every one of us knows how to speak our language. No problem. Okay. And for a couple of thousand years, every culture, or many cultures, have a written language. Okay? And the written language, well, there's many different types of written languages, but for most of mankind, what they had was called a symbolic hieroglyphics, okay, which basically consisted of the following. For every spoken word, there was a signal, a sign, that corresponded to that. So if you spoke this word, you had this written sign or chiseled sign or scratched in sign. They used to scratch it in on a piece of mud. Okay, you had that sign. So again, to every word there was a sign, and if you wanted to tell a whole story, the whole story would consist of a lot of words in some type of order, and so you would have a lot of symbols. And you can see those, you can see them in ancient Egypt, but you can also see them today in Chinese, Japanese, and Korean. They use symbols. Okay, very good. About 2,500 or 3,000 years ago, there was a little place here called Assyria. Or around there. And they had this idea. They said, you know what? Oh, let me just, before I go further, there's a problem with hieroglyphics. The problem is that if you want to communicate with someone else, even if they speak the same language as you, that other person has to know every symbol that you're going to use. So if you're going to have a symbol, okay, for a tree, then they have to have the same symbol for the tree. If you're going to have a symbol for lasagna, then they have to have the same symbol for lasagna. Okay, otherwise you can't communicate with them. It's great. Okay, so again, the word lasagna exists. Everybody can talk. Everybody knows what lasagna is. Everybody's thinking about lasagna. Okay, but the symbol might not be known by two people, and so it might be harder to communicate. Now, in Assyria, they had the following idea. Someone had the following idea. He said, you know what? I don't want to give a sign for a word. I want to spell out the word. For example, I don't want to make a symbol for a shoe, okay? Instead, I want to make the sound shoe, okay? And the sound shoe is, you know, well, let's see. That looks like teeth, and teeth makes the sh sound, okay? And that makes the oo sound. So shoe, I have it right there. Okay, and if I want to make a ship, rather than drawing the picture of a ship, I'm going to make the shoe sound again, the sh sound again, and then, I don't know, an I sound, sh, and then a P sound, a P sound. So they had this idea that rather than having for every word a symbol, okay, have a few different symbols, and I mean a few by like about 20, 25 symbols for different sounds. And then the words are just spelled out like that. And then, again, the word lasagna, instead of having a symbol for lasagna, I'm going to make a symbol for the L sound, then I'm going to make a symbol for the S sound, and then I'm going to make the symbol for the sound, and then I'm going to make the symbol for the N sound, and then I'm going to make the symbol for the sound. Lasagna. I spell it the way I want to spell it. Okay? So that idea happened here. Okay? And so what they had was, they had a few different symbols, which we just defined as an alphabet. Okay, we just defined that as an alphabet, and we had those symbols to be the different sounds that it corresponds to. Okay, the different sounds. And then what we needed to do was, for every word, there's a permutation of those sounds, and so there'll be a permutation of the symbols to do it. So for example, car is an English word, okay? For us New Yorkers, we call it a car. It only has two symbols, C and O. But for non-New Yorkers, those poor people, they have car. And so instead of drawing a picture of a car, okay, with four wheels, what we do is we make three letters sounding out the word car. K, R. Makes sense. And for the word bat, instead of drawing a picture of a bat, okay, I write B-A-T. Okay, so that's an amazing innovation. That's an amazing innovation. Again, let's just go through what that innovation was. Rather than having for every spoken word or every concept having a symbol, we have for every spoken word, we have a sequence of letters which corresponds to sounds. We have the word. Okay? Now this idea happened over here, and then it was spread because it was a good idea. Why is it a good idea? For the following reason. If I want to communicate with someone else who speaks my same language, I don't have to give him thousands of different symbols. I don't have to share with him thousands of different symbols. I have to share with him 25 different symbols, which corresponds to the 25 sounds. And then from the rest, we could communicate easily because we can sound out the words, and he can sound out the words, and there's nice communication. By the way, not all words have one symbol. For example, in English, we do SH, makes the sh sound. And TH makes the th sound. And GH makes, well, could make the F sound. Okay? And it's even more complicated because sometimes two different symbols can correspond to the same sound, like a soft C and an S. Okay? They can make the same sound. Or a hard C and a K. Those two symbols can make the same sound. So things get a little bit more complicated. And an A and an E sometimes can be confused, etc., etc. Okay. But this was a vast improvement because it improved communication tremendously. Why? Because in order to communicate with someone, I only have to share with them 25 symbols, and then they can sound it out the rest. So it worked. Okay. So this idea was a good idea. It went to Hebrew, and here the Hebrew alphabet was called Aleph, Beis, Gimel. Okay. It also went to here, where Phoenicians and Philistines lived. They were basically boat people, and that the idea traveled around from there. It went to Greece, and they have Alpha, Beta, Gamma. Alpha, Beta, Gamma is Aleph, Beis, Gimel. Okay. It went down here to Arabia, and you have Abj, which is the Arabic alphabet. Italy at some point takes over Greece, and they have ABC. They see this idea and they say, hey, this is a great idea. ABC. Again, ABC is like Alpha, Beta, Gamma. Okay, so it's the same thing. And by the way, the word alphabet is Aleph, Beis. Alpha, Beta. Okay, it's just the first two letters of this set of alphabet that's used here. Anyways, the Latin alphabet is gotten here, but again, at the time, Rome is controlling the world. In particular, it goes to England and Spain, okay, and they're using this idea. And the idea is as follows. Any culture that meets this idea says, hey, this is a good idea. We have a language. Let's find an alphabet that we can use, that we can sound out the words. Okay? Now, it didn't conquer the entire world. There's a lot of cultures out east that you still use pictures, but it conquered a large part of the world, and it's an ever-changing thing. Here's one idea to keep in mind. Now, this seems like an obvious thing. This seems like a great invention, and everyone should love this, because rather than having one symbol for one concept, you just have a permutation of a few symbols for one concept. That's a great idea. The thing is, and it seems obvious to us now, the thing is, that idea only happened once. As far as I know, that idea only happened once. It happened here, and it was spread around throughout the Western world because it happened there. Now, here's something to think about. Let's say the guy or girl who was thinking of this idea in Assyria, okay, and had this great idea and was walking to the patent office and saying, hey, this is a good idea. I'm going to save a lot of memorization by just having a few symbols. This is a great idea. I'm simplifying it. Obviously, this was a process that took hundreds of years to formulate, whatever. But let's say that person was walking to the patent office to patent his idea or her idea, okay, and the person tripped, okay, hit his head on the stone. The idea never happened, okay. Question: would the idea have shown up anyplace else? And I can tell you, it's a question. I have no idea how to answer that question, but I can tell you it showed up no place else in the world. In other words, every single country, every single culture has spoken word. Many cultures have written word. If they didn't get the idea from here, they didn't invent this idea by themselves. So that's a very interesting transformation. That's a very interesting transformation. It only happened once. Could have happened again. Okay, maybe if it didn't happen here, it would have happened here, and everyone would have spread it, and that would have been a great idea. Could have, but it only, as far as we know, it only happened once. Anyways, that's something to think about. I remember just reading that and being shocked by that. Okay, so next class we start talking about finite automatons and simple languages called regular languages. Thank you very much.